This morning session, so the first topic given by Yvon Bardet about decoherence samples in open quantum systems using non-commutative functions.
Okay, thank you, Robert. So first I would like to thank the organizer for this opportunity. It's my first time I view on I.I.D. and it's a very nice workshop. Okay, so I'm going to talk about tools in order to estimate the time of decoherence. So I have two articles on this, and the second one is a joint work with Cambis-Rosé, the one in blue. Okay, so the basic idea, I think, behind decoherence is the following one. So I will present this, and this will be my toy model for all the talk. So we have a quantum system, a d-dimensional quantum system that I write H, and I will write d of d is a set of density matrix on H. So I think the most shared ideas behind decoherence is the fact that in your system you have a preferred basis, and if you start with any state, you write it in this basis, and you will have off-diagonal terms. And decoherence is the fact that these off-diagonal terms, they will disappear due to the effect of the environment. And so in the end, you start with any row, and in the end you find something which is diagonal. So in a sense it is classical because they are all diagonal in the same orthonormal basis. So I want to study the speed of this process. So in order to do it, I need some interpolation between those two states, and a very easy way to do it is to introduce this family of rho t in this way. So I put an exponential minus t in front of rho and 1 minus exponential minus t in front of its projection on the diagonal part. So I indeed have that for time t equals 0, I start with my state, and for time t equals infinity, I project it on the diagonal part. So now I can define what I call the decoherence time of this process, and it will be the first time such that for any row I find that at time t I'm close to its projection up to a distance epsilon. Something which is important here is the fact that I choose the one norm, so the trace distance. Of course, because here I'm talking about a phenomenological idea of decoherence. I'm talking about why we don't see quantum effects as a classical observer. And what we can do as a classical observer are measurements. And the way to quantify the distance based on measurements that we can do is the trace distance. Okay. So, the remark here is that rho of t here is a special instance. It's an example of a quantum Markovian evolution. So the main point of this works is to extend tools that could work for any quantum Markov semigroup. So in the first part, I will introduce the quantum Markov semigroups, and I will introduce a notion of decoherence for generic quantum Markov semigroups. In the second part, I will introduce the basic tools that we can use in order to estimate the decoherence time. And this will lead us to the notion of LP irregularity, which is important in the study of those functional tools. And also to the notion of hypercontractivity. And finally, in the last part, I will, if I have time, I will present the result we have with Cambis-Rosé, which is on hypercontractivity for non-primitive quantum Markov semigroup. I will explain, of course, what it means. Okay, so first, what is a quantum Markov semigroup? So I'm sure you all know what it is already, but it will help to fix the notation. So in the Markovian regime, you know that the evolution of an open system can be modeled by a quantum Markov semigroup. So it's a semigroup of superoperators of quantum channels, more precisely, that I write PT dagger. So they satisfy the semigroup property. So they map state into states, and so they preserve the trace. Okay, so they are completely positive, they have the semigroup property, and they preserve the trace. And because of the semigroup property, and because we are on a finite dimensional space, we know that we can write our semigroup as the exponential of some operator. And this operator is called the Lindbladian. So we know the specific form of the Lindbladian, but I will not use it, so I will not introduce it. Okay, so this is in the Schrödinger picture. I was describing the evolution of states, but we can also describe the evolution of observables. And to do that, we use duality in the Hilbert-Schmidt scalar product. So we can introduce the dual of PT dagger, which I denote by PT. And this time the dual is still completely positive and semigroup, but instead of preserving the trace, it will preserve the identity operator. And the main assumption that I will make all over this talk is the fact that there exists a full rank invariant density matrix sigma. So the fact that it is invariant, you can see it either in the Schrödinger picture by saying that it is preserved by the evolution, or you can also see it in the Heisenberg picture by saying that the average of any observable stays the same along the evolution. Okay, so just to repeat myself, PT dagger will always be for the Schrödinger picture, and PT without the dagger will be for the Heisenberg picture. Okay, so now I would like to describe the asymptotic behavior of such semigroup. And in order to do that, I need to introduce what is called the decoherence-free algebra. So this algebra is the largest subalgebra of all the observable, on which the evolution is a unitary. So what I mean by this is that if I take an observable in this algebra, it will evolve in a unitary way. The quantum Markov semigroup is now like it evolves as a closed system, and you can see that such evolution will be the solution. Such an evolution will be the solution of the Heisenberg equation for closed system. So the way to see it is that inside your big system, which suffer from decoherence effect, from nodes from the environment, there is a smaller subalgebra, a smaller system, which is preserved from the nodes. Okay? And because I assume that there exists a full rank invariant density matrix, and I didn't say it, but here the hypothesis, the important hypothesis is that it is full rank, it is invertible. Because there exists such an invariant density matrix, there exists a conditional expectation, or you can see it as a projection from the whole algebra to this smaller algebra, to this smaller decoherence-free algebra. And also, if you look at the evolution of an observable minus its projection, this will go to 0. So in a sense, you converge towards this algebra. But I have to keep the PT outside because inside the algebra, this En of x, it still evolves in a unitary way. So maybe I can do the picture. So it's a wrong picture because I cannot draw matrix on a plane. But like, if this is N of P, on N of P I evolve in a unitary way, but if I start outside, I will rotate like this, but still converge towards the decoherence-free algebra. Okay, so it's convenient to prove this result in the Heisenberg picture because we have all the tools coming from operator algebra theory. But we can, once we have proved it, we can also state it in the Schrödinger picture, and it's exactly the same. You can define the dual of the conditional expectation E of N, and you have the same kind of convergence. Okay, so intuitively, PT of x, it interpolates between x and its projection on the decoherence-free algebra. Okay, so I will give two examples. So the first one is a class of example, is a case where there is a unique invariant state. And in this case, the decoherence-free algebra is trivial. There are only the multiple of the identity operator. So there is a unique invariant density matrix. And because of this, the conditional expectation is just taking the average under the observable, and the dual one just project on the invariant state. And the limit I wrote before, we can write it in a very simple way. So any state will converge towards a unique invariant state, and any observable will converge toward its mean. Okay, but another example is one I gave on the first slide, and we can generalize it a bit. So here I wrote that n of p is the algebra of diagonal operators, but you can see here in the definition that it does not depend really on the specific form of the algebra. You can take any conditional expectation and define an operator like this, a Lindbladian like this. So here En and his dual are equal when in the case of the diagonal operators. And in the general case, you can always solve the Baster equation for this Lindbladian, and you find this following evolution, which is very similar to the one I gave in the first slide. The only difference is that I can take any conditional expectation. And still in the case where the algebra is the algebra of diagonal operators, we know that a full rank invariant density matrix is given by the maximally mixed state. And again, the limits before can be rewritten in this way as the fact that you converge towards the projection. So here, you don't have this unitary evolution which is left, which is why I can put the limit on the right side. Okay, so actually in general, we know what is the structure of the decoherence-free algebra because it is a star subalgebra of B of H. And the structure of such algebra is well known. So you can decompose your Hilbert space in a direct sum of some subspace Hi, and each of these Hi's appears with a multiplicity Ki. And now the decoherence-free algebra is a direct sum of the observable on Hi. And when you have one observable on Hi that appear, it will appear with multiplicity Ki. It will appear Ki times on the diagonal. And so if you take any observable in this Hi, because it is in the decoherence-free algebra, it evolves in a unitary way. And I think it is why this algebra is called the decoherence-free algebra, because it encodes all the inside it, you have all the information on all the decoherence-free subsystems. So the Hi here, they are called decoherence-free subsystems. And they were studied by many people, so I took one group that studies them, so Campe, Bacon, Lida, and Welle, in around 2000. And they studied such decoherence-free subsystems because they thought they were good candidates in order to have fault-tolerant universal quantum computation. So they thought that maybe we could try to encode some states in this Hi, and doing this, they will not suffer from decoherence. So if you know the noise that act on your system, you can model the noise with quantum Markovian evolution. You can find the decoherence-free algebra, and then you can encode your states in the part that does not suffer from decoherence, which for quantum computation would be great. So unfortunately, I think it's very difficult in practice to do such a thing. Okay. So just to summarize this section, so open quantum system can be modeled using quantum Markovian semigroups. When there exists a full rank invariant state, and I insist on the fact that it has to be full rank, we can define the decoherence-free algebra. It is the algebra on which the evolution is not anymore a dissipative evolution, but a closed evolution. And there always exists a conditional expectation that projects on this subalgebra. And so we have those two limits. And now the goal is to study the what I call the decoherence time, which is a generalization of the definition I gave in the first slide. So it's exactly the first thing. You look at the first time such that the distance between a state and its projection is smaller than epsilon for all states. Okay, so the basic idea that we will use is the following one. So we will use, I want to use Lyapunov functional. So what are they? So I will introduce them first in the Schrödinger picture. So a Lyapunov functional is a functional that acts on the states and that maps them to to a real number, and such that first they are zero if and only if rho is equal to its projection, so if you are already in the decoherence-free algebra. And furthermore, they are non-increasing along the evolution. So, and I will call a good Lyapunov functional if I can control my trace distance, my one distance, in terms of this Lyapunov functional with a good f of t, of course. So the goal is to, instead of having to estimate this trace norm, the goal is to estimate instead some other distance, which is nice property. It will not be a true distance, but it will serve as a distance with nice property. So of course it has to vanish only on the correct set, and also it is non-increasing. Okay, so you can do the same thing in the Heisenberg picture. So we will ask the functional to be zero only on the decoherence-free part, and we will ask it to be non-increasing. And the thing is, because it is non-increasing, we know that if we differentiate it, we will find a negative quantity. So now if we define E, the functional, the energy functional E phi of rho as a minus the derivative, and if we define the functional inequality like this, so here we have a functional smaller than minus its derivative. So we can integrate this inequality and we find an exponential convergence in terms of this functional. Okay? So this is what we call functional inequality, and this is the kind of functional inequality that I was speaking about in the title of this talk. Okay, so we will do this for true Lyapunov functional. So first I recall the definition of the decoherence time. So the two Lyapunov functionals that we will use, so the first one is a chi2 divergence, and the second one is a relative entropy. So the first bond was derived, I think, by Ruska in '94, and then it was reproved some years later for generalized Q2 divergence. And the second one is Pinsker inequality. What will be also relevant later is that we can find universal upper bound of the Q2 divergence and the relative entropy in terms of the second state. And for the first one, we find an upper bound has 1 over sigma mean, the smallest eigenvalue of sigma. And in the second time, we find something of log of 1 over sigma mean. And we will see that this log here will make the second inequality more powerful than the first one, more interesting than the first one. Okay, so we have two Lyapunov functionals, the Q2 divergence and the relative entropy. So I will start with the Q2 divergence. So first I need to introduce some notation. So actually in the general case, when the semigroup is not primitive, there are a lot of invariant states, so I need to pick one as a reference invariant state. And the one I pick is the projection of the maximally mixed state. So this state has very nice property. For instance, it is tertial and it commutes with any element of the decoherence-free algebra. Okay, so with respect to this state, I can introduce a scalar product, which is I think called 1/2 scalar product, because we split the state in two. Okay, and if I write p hat, the dual of p, for this scalar product, then we see that pi hat describes the evolution of the relative density. So this is what I call the relative density of a state rho. And you know, most of you know that pi hat is actually the Petz recovery map of P for this scalar product given by sigma trace. And so this reflects into the fact that it gives the evolution of the relative density. Okay, so now if I write x, this relative density, my Q2 divergence, I can write it exactly as the two distance between x and its projection, the square of the two distance. So actually the Q2 divergence has a L2 space signification. And the bond I had before, I can rewrite it as just a bond between a 1 norm and a 2 norm. Okay, and I do this because it's easier to work with now this 2 norm and this P to work in the Heisenberg picture. So I will do what I explained, what we can do with Lyapunov functional. So I introduce minus the derivative of this Lyapunov functional, and this is called the Dirichlet form. Actually, it is defined independently of the fact that it is the derivative of this. And now I can introduce the decoherence, what I call the decoherence-free Poincaré inequality, which is the functional inequality I introduce for any Lyapunov functional, but specialized to this Lyapunov functional. And I'm sorry, there should be a square here, because the Lyapunov functional is really the one with a square. Okay, and as I explained, if this inequality holds, then we have an exponential convergence in terms of the 2 norm. And something very important here is that using this inequality, we can prove that actually the best constant in this inequality, which is defined like this, is also the spectral gap of the symmetrization of the Lindbladian. So it is a spectral gap of L plus its adjoint over 2. So it means the gap between the eigenvalue 0 and the second biggest eigenvalue of L. And because of this, because also we are on a finite dimensional space, we know that the spectral gap is positive. So we know that we have effectively the exponential convergence. Okay, so now I do the same thing with the relative entropy. So if we derive the relative entropy, we find what Spohn defined as the entropy production, and what Marius called the Fisher information during the open questions. We have a nice expression for it, and actually we can write it in terms of the sigma trace. Okay, so we can define a functional inequality, which I call the modified Log-Sobolev inequality, and that's the one that Marius calls the Fisher Log-Sobolev inequality. We can define it in this way, and for the same reason, if this holds, then we have the exponential convergence in terms of the relative entropy. And as an additional result, we know that this is smaller than the spectral gap. And for the moment, I will not say anything about the fact that it is positive or not. Okay, so we can illustrate this on the decoherence QMS, so the one I gave as an example. So we have this quantum Markov semigroup, and actually we can compute quite explicitly the Fisher information, the entropy prediction. And using this, we can prove that the Log-Sobolev constant is always bigger than 1/2, so it is positive. And then we can put everything back in the bound we had for the trace norm. And so with the first one, we find something which is exponential times the square root of d. And second one, we find something which is square root of log d. And now if you compute using this the decoherence time, you find something which is, for the spectral gap, you find something which is of order log d. And for the Log-Sobolev inequality, you find something which is of order log of log d. So you really improve your estimation on the decoherence time using the Log-Sobolev inequality. Okay, so a small summary of this section. So it was really important in what I did to define the reference state to be these states. And also, so here what I did is generalize functional inequalities that were defined for primitive semigroup, and I generalized them to non-primitive evolution. And it's a bit hidden in what I did, but one of the main points was to replace each time that you have a distance between a state and the invariant state. One of the main idea was to replace this distance by the distance between a state and its projection. So when sigma appears, you have to replace it by its projection. And again, we find that, as in the primitive case, the modified Log-Sobolev inequality can prove by a logarithmic factor the estimation of the decoherence time compared to the Poincaré inequality. Okay, so now the question I elude is the positivity of this constant. So how do we know that this constant is positive? So one way to see that it is not trivial to prove it is the fact that we know when the relative entropy is 0. It is for the invariant state, or not the invariant state, but the one that are equal to the projection. But in general, we don't know what is the zero set of this entropy prediction. And this was defined maybe 20 years ago, and we still don't know in general what is the zero set. And if we want this inequality to hold, we need that the zero set is exactly the same as the one for the relative entropy. If not, you can find one state such that this is zero and not this, and it fails. Okay, so one tool that I find in order to prove this fact, this last fact, so this is the L1 regularity. I mean, it was defined way before. So the L1 regularity states that the entropy prediction is is the Dirichlet form, which is here. This was the derivative of the two norms, is dominated by the entropy prediction. So of course you have to change a bit the quantity in order to make them. I mean, this is a L2 quantity and this is a L1 quantity, so you have to make this into a L2 quantity. And if you have such an inequality, if this is zero, then this is zero, and we know the zero set of the Dirichlet form, and it is the correct one. Okay, so this property is always true for classical Markov semigroups. And unfortunately, in the quantum case, it was proved only for several examples, so for unital and twice-preserving quantum Markov semigroup, for Davies semigroup, and for the depolarizing semigroup. And we will give later a general sufficient condition in order to get this, and which include all the known case. Okay, and now what I said is that if the quantum Markov semigroup is L1 regular, then the zero set of the entropy prediction is the correct set. Okay, so why does it help, this condition? So recall that for the modified log-Sobolev inequality, so we have this inequality here. So now, using the L1 regularity, we can study instead this inequality here, because the L1 regularity says that more or less this is smaller than this, so we will have the entropy prediction here, so we will have the inequality we want. So it means that the constant that appears in this inequality is always smaller than twice the constant for this inequality. So why is this inequality easier to deal with? So first, let's give it a name. So let's give it its correct name. So this inequality is called the true logarithmic Sobolev inequality. It is actually the first log Sobolev inequality, the one defined by Gross in 1975. Okay, so I use some relative density of rho just to rewrite everything in a nicer way. And the thing is, this inequality can be completely rephrased in the language of non-commutative LP spaces. So that's what I will do now. So first I need to introduce some LP spaces. So I take a full rank invariant state, full rank state, and I define LP space in this way. And you see that the L2 space is the one given by the scalar product before. Okay, so I will need this notation. So a natural map to go from one space to the other one is this EQP. So don't focus too much on the definition. Just keep in your mind that it is a way to go from one LP space to another LQ space. Okay, so these norms have nice properties, so they are dual to each other if you take conjugate parameters. They compare to each other in a nice way also, and the semigroup is always contractive for those norms. Okay, so for this slide and the following one, I will assume that the semigroup is primitive, and so I have a unique invariant state which I denote by sigma again. So I recall the definition of the true entropy, which is this one, for where rho is a density matrix that you cook up with thanks to x. Okay, and the thing, what I said before, is that both the entropy, relative entropy, and the Dirichlet form can be rewritten in terms of this LP space. So more precisely, and actually we can generalize this definition for any p, not only p equal 2. If you differentiate the p norm, or pt of x of the p norm with p fixed and t, and you differentiate with respect to t, you find a P-Dirichlet form. So don't focus on what is in front, but just we find something which corresponds to a P-Dirichlet form. But if instead we fix x and we differentiate with respect to the parameter q, p here, and we differentiate at q equal p, we find a p entropy, which is defined in a similar way as the true entropy. And what Gross did, the right idea of Gross in 75 was to take a simultaneously derivative of the two quantities. So he finds that if you take p of t, which is equal to this precisely, and if you differentiate simultaneously the time evolution and the parameter of the norm, you find such quantity here, and here you can see that it's very close to the log sub F inequality. I mean, it is the two terms of the log sub F inequalities. Okay, and I just proved the following theorem, which was proved in the quantum case by Olkiewicz and Zegarlinsky in 1999. So I just proved that if a semigroup satisfies such an inequality, if I take p of t of the same form, so here I take p equal 2 compared to the previous slide. If my semigroup is hypercontractive, so it contracts from the L2 space to the LP space, then I have this P log sub F inequality. Just by deriving what it means here, I obtain this log sub F inequality. And conversely, if I have this inequality for all P, I can integrate this and I find back hypercontractivity. Okay. One very important remark here is that I need, in order to have the equivalence, I need this inequality to be true for any p. If not, I cannot integrate it back. And again, a way to have only one inequality is to use some regularity of the Dirichlet form. So this is the content of the following theorem. So if the semigroup satisfies this commutation property, so if it commutes with the modular operator of the invariant state, sigma trace, then you can prove LP regularity, which is just a comparison between the L2 Dirichlet form and the LP Dirichlet form. And this includes the L1 regularity I introduced before in the case where you take the limit p goes to 1. Okay, so this is the most general situation under this hypothesis, but if furthermore you assume that the semigroup is reversible, so it is equal to its adjoint, then you can also prove a stronger form of regularity, so the semigroup is strongly LP regular, which is just some stronger inequality than the one before, but it's still a comparison between the 2 Dirichlet form and the P Dirichlet form. And there is also another generalization of this inequality, which is called the Stroke-Varapoulos inequality, which was proved by Beigi, Data, and Rose. And here I only compare the two Dirichlet form with the P Dirichlet form, but you can also compare the P Dirichlet form with the Q Dirichlet form when P and Q are smaller than 2. Okay, I introduce this because I think Cambis will use it in his talk. Okay, so now just using this inequality here, you can prove the equivalence between one log sub F inequality and hypercontractivity. And using the case p equal 1, maybe I have it here, sorry. So, yeah, so using the case p equal 1, so L1 regularity, if we are able to prove that this inequality holds, then we have proved that our constant was positive. The modified log sub F constant was positive. Okay, and for primitive quantum Markov semigroup, we actually know that this constant for this inequality is positive. And the way to prove this is to use the equivalence with hypercontractivity, then use interpolation techniques to prove hypercontractivity. But unfortunately, hypercontractivity in a weak sense, but then you can use some uniform convexity of the LP norms, some very strong inequality of the LP norms, in order to get back hypercontractivity. And once you have hypercontractivity, you have the log sub F inequality. So in the primitive case, there is a whole machinery using hypercontractivity in order to prove that this constant is always positive. Unfortunately, what I will say in the last 5 minutes, what I will explain in the last 5 minutes, is the fact that if we generalize the notion of hypercontractivity to non-primitive semigroup, we find that this constant is always equal to 0. So this whole very nice machinery, we cannot use it for non-primitive evolution. But nevertheless, what I was able to prove was that directly, if you assume this commutation relation between the modular operator and the semigroup, then the modified Log-Sobolev constant is positive. Okay, one last remark. So there is one particular example of non-primitive evolution which is really interesting, even for primitive Markov semigroup. So if you have a primitive Markov semigroup, quantum Markov semigroup, you can be interested in its tensorization. So if I define Ln the Lindbladian of this tensorization, what you can prove, I think Henri and Marius will explain this in more detail later, so I will be very quick on this, but what you can prove is that the modified Log-Sobolev constants of the tensorized semigroup is always bigger than some constants that appear some constant for some non-primitive semigroup. So I will put all the slide. Okay, so what this is here is the Lindbladian for one copy of the semigroup, and you regularize, like you put identity, tensor identity with what is left. And now this becomes a non-primitive semigroup, and you can define the modified Log-Sobolev inequality for this semigroup. And if you are able to control for all k this quantity, then you find a Log-Sobolev constant for the tensorization of the semigroup. Okay, and I think, so this was the open question of Marius was, is this constant positive or not? So for the moment, we really, except for a lot of examples that Marius will explain, we really have no clue at all for the general case. And the most general result we have, which is very weak, we will see, is that if the semigroup commutes with a modular operator, it is also true for its amplation on the tensor product. And in this case, for all k, the Log-Sobolev constant is positive. So we know that for all k it is positive, but we don't know at all how it behaves when k goes to infinity. Okay, so just to summarize, the positivity of the modified Log-Sobolev constant is still an open problem. Actually, it's as open as in the primitive case, because in the primitive case, we need L1 regularity. And we only know L1 regularity for the case that when we have this commutation relation. So what I find interesting is that just trying to prove the Log-Sobolev constant without using hypercontractivity make it apparent that this commutation relation with the modular operator is very important, and we don't know how to do when we don't have this commutation relation. And we are really lacking of techniques, that we really don't know what to do. And actually, we know of an example where we don't have this commutation relation, but still we know that the zero set of the entropy production is the correct set, which is okay. And we don't know of any example where the commutation relation does not hold, but where the entropy. Okay, I said this. So we don't know of any example where where we don't have this commutation relation, and where the Log-Sobolev constant is positive or not positive. Like the question is really open. Okay, so apart from very simple example, what was left from what I explained before is how to obtain estimate on the Log-Sobolev constant. And in the primitive case, one way to obtain such estimate is to use again hypercontractivity. So that's why with Camille-Rosé we start to study hypercontractivity, so I will be... Yeah.
You say you know of an example, we do know of an example, or do you mean to say we do not know?
So we do not know of any example where the constant is positive, but we don't have the commutation relation. We also don't know of any example where the constant is not positive. So we know outside of this commutation relation, we know nothing. Yeah. Okay, so very quickly, so if we want to study hypercontractivity with for non-primitive semigroup, we need another norm, because hypercontractivity for the norm I defined before imply the fact that the semigroup is primitive. And the norm we find was the most appropriate to do that are the amalgamated LP norms defined by Marius and Javier Parce. Okay, so they are defined in this variational way, and it's a bit difficult at the beginning, but after 1 or 2 years you can get used to it. So they have all the nice properties that we need in order to study hypercontractivity. So I will just skip this. And with respect to this norm, we can define hypercontractivity. So first I recall the definition of the Q entropy and the Q Dirichlet form. And here I will need a more general definition of fluxable inequality, where I had this term here with the constant d. And in the same way, so we can define hypercontractivity, and instead of asking the semigroup to be contractive, I will relax this, and I will ask just that it has a constant which behaves like this. Okay, and so we were able to prove, following the proof of Bézier and King for the completely bound norms, we were able to prove for the amalgamated norms, the gross lemma, so the derivation of the differentiation of the norms. And we find again the same quantity. And so this is also why we know that the quantity we defined before are the correct generalization. Okay, using this you can prove that hypercontractivity implies Log-Sobolev inequality. But it's very difficult to integrate this, because here the derivative only works for P0 equal Q. We cannot differentiate for any parameter. But what we were able to prove is that Log-Sobolev inequality implies hypercontractivity, but with another constant which does not appear in the primitive case. And it is the number of blocks in the decomposition of the decoherence-free algebra. And also the other difference compared to the primitive case is, as I said, that if you have Log-Sobolev inequality, then the weak constant, the constant d, has to be positive. Okay. And finally, so we cannot use the Lyapunov functional technique I explained before to obtain estimate of the decoherence time, but we can still use other techniques, interpolation techniques, and obtain using hypercontractivity directly, and not the Log-Sobolev inequality, but hypercontractivity directly. We can still prove some estimate of the decoherence time. And there is still a third difference with the primitive case, which is that there is a constant that appears, which again depend on the decoherence-free algebra, so it's the dimension of the maximal subspace. And the fact that this constant appears, we still don't understand this very well, but this is a problem, because you see that the bigger the decoherence-free subsystem are, the longer it will take for the semigroup to converge. So if you want to encode your information in some decoherence-free subsystem, you want it to be as big as possible, but you also want the decoherence time to be as fast as possible. And this shows that you have to pay a price to have the system as big as you want. Okay, so to summarize, we generalize the notion of hypercontractivity to non-primitive semigroup using the amalgamated LP norms. Unfortunately for application, but very interestingly from a mathematical point of view, the tight version of hypercontractivity always fails for non-primitive semigroup. And this can be interpreted as a lack of convexity for the amalgamated norms. So I said that in the primitive case we need some strong convexity property of the norms. And the fact that the Log-Sobolev inequality fails shows that we don't have this property for amalgamated norms. And I think this result were was not known before. Okay, and there are also some other differences that occur compared to the primitive case, and those differences appear as constants in different parts. Okay, so to conclude, we propose a framework in which we can study the decoherence time of a quantum Markov semigroup using functional inequalities. And among other things, this framework is also the good framework in order to study the tensorization of the log-Sobolev constant. And so some open problems. So first we need some techniques to obtain estimates, and I said that this is not so an open problem because Marius will talk about the technique he developed in order to obtain estimates. We also have a work in progress on quantum application in quantum information theory. So actually we can use hypercontractivity on all these estimates to obtain bond and capacities, but still ongoing projects. And the truly open question is, what can we say about this log-Sobolev constant outside of the commutation relation? Okay, thank you.
So the firstly, you said you showed that this tight version of the hypercontractivity phase,
Mm-hmm.
and it's interesting. But could it possibly be that you use these amalgamated LP norms? Could there be some other norms under which it would be tight, or is that?
So it's a very good question. I mean, if you want really have to use all the LP space structure and everything, I think they are the correct norm. They are really the norms that you want, because they are interpolating family of norms, and they have all the property we want. So I think yes. So maybe Marius will have another opinion on this, but I would say that they are the perfect norm for this. Yeah.
So you think this is an unavoidable feature, this lack of tightness?
I mean,
and, one other question. You know, this open question that you said. Can you give me an example of a quantum Markov semigroup where this commutation relation is not satisfied with the module operator? That would make this question more interesting, right?
Do you have 5 minutes?
Okay, afterwards.
Yes, we have example.
Yeah.
So if you were to constrain yourself to this decoherence-free subspace.
Sorry?
So when you do quantum computation in this decoherence-free subspace, do your results give any bounds on the depth of the circuit you can run?
We have not thought about it. Good question. I don't know. For the moment, we don't see how to connect the estimation of the decoherence time with properties of this subspace. So, yeah, that's a good question.
I don't have 1 to 2 years, but we have a few minutes.
So you showed these relations to expressions which are essentially entropic quantities.
Mm-hmm.
So in the case of entropies, we usually have some constraint, or we have some, let's say, the sigma that appeared in your slides. It is often not the most general, let's say, state one could write down. It often has something like, for example, an identity on one subsystem and the marginal of the state.
It's because sigma is a non-variant state.
Sorry, is that?
Is a non-variant state. So when you apply the semigroup, it's still sigma.
Yes. So I guess this is probably reflected by the fact that if, like, the sigma that appears in let's say expressions when we define conditional entropies or mutual information has also certain. Okay, I cannot really match it precisely, but it has certain invariant properties because it's defined by marginals. But I'm wondering whether you can kind of exploit the special structure we have in quantum information to, let's say, make statements in the cases where they are not possible.
So maybe I can just make a comment on this. Yeah, so here, for instance, okay, here. In this inequality, what you can say is that, so in all your result on recoverability and everything, what appears is that you need a rotated recovery map. And the recovery map appear somewhere here in this inequality. And so I tried using all the techniques you develop. I mean, each time I read a new article, I tried the techniques that were inside to prove this inequality using these techniques, or to prove LP regularity. And so far, I have not succeeded. But yeah, I think it's the correct way to see it. I think there will be some rotated version at some point.
I think we should move on to the next step. So let's thank you all again.